So in this video, we're going to look at how we generate radicals during the course of a reaction, and then the types of reactions that those generated radicals can undergo. So again, the stuff we were looking at in the last lecture were reactions that were that involved radicals that were added at the outset of the reaction. But most radicals are generated in situ. So in situ, or during the course of the reaction. So the first example we could look at is homolysis of diatomic molecules, where we have, in this case, we have Cl and Cl reacting under heat or light. This is chemistry that we've talked about in Organic 1, where if we have some diatomic halide like chlorine, bromine, or iodine, we treat those with enough heat or light, they will split apart under a homolysis reaction to generate two radicals, in this case, chlorine radicals, as I have drawn. So it turns out that and the reason why is because we have basically two giant elements that are trying to bond with each other. So it's a weak bond. It undergoes bond dissociation with not too much energy. But there are other strained or unstable sigma bonds that can undergo homolysis. So other strained / unstable sigma bonds that undergo homolysis to generate free radicals. So these include cyclopropanes, for instance, especially when the cyclopropanes could undergo homolysis at one of their bonds to generate stable free radicals. In this case, we have the radicals are actually positioned at benzylic carbons. So the addition of those phenyl groups, those benzene rings, is really critical. Now, if you recall, when we were talking about drawing bond line structures and Lewis structures in the early days of Organic 1, I said, let's avoid peroxide intermediates, or peroxide structures in your proposals. It was because these peroxides, I'll label them here. It's because these peroxides form an unstable sigma bond and are prone to homolysis in the presence of heat, which is why if you are handling them, you want to avoid exposing them to a heat source, just because peroxides are readily formed in the reaction of oxygen with certain species, diethyl ether in particular, a pretty go-to solvent, especially like 20, 30 years ago. Now is not used as often, I would say, as things like ethyl acetate, and that's because diethyl ether readily reacts with oxygen. You have to be wary about and careful about how old a bottle is getting, because it's the hedge space exchanges with oxygen. Oxygen can react with diethyl ether to form peroxide intermediates. These things readily break down to form an oxide free radical, which we know is unstable and likely to undergo other types of reactions. Now, you can make this a little bit less of an issue if you attach these things to, if you put the peroxide into an electron deficient next to an electron withdrawing group. So acyl groups provide some stability to oxide radicals, which is why I much prefer benzoyl peroxide to a dialkyl peroxide. Now, hydrogen peroxide, you might think, goes in the opposite direction, but typically hydrogen peroxide is handled as a solution in water, whereas the other peroxides I'm kind of alluding to can actually be acquired neat or without being diluted in solvent. Benzoyl peroxide is typically dissolved, I think, in a phthalate structure, but here's our BZ, or our benzoyl group. So we have our peroxide in the center surrounded by two BZ groups. Now, we actually handled MCPBA in organic too. We're not this year, unfortunately, due to COVID, but MCPBA is metachloroperoxybenzoic acid. We put that acyl group on our peroxide, but that allows for the epoxidation of alkenes, where you convert alkenes into epoxides. Okay, so far, these sources of radical intermediates have been a little bit of an issue to work with. Benzoyl peroxides are better, but they could be safer yet. We've got some cyclopropane radicals that are formed, but requires pretty special circumstances. And then dihalides can undergo a ton of side reactions, which makes them problematic to use. But there are some more robust systems for generating free radicals during the course of a reaction, which we can use to have more productive endpoints, let me just say. So we have AIBN, azo, bis, iso, butyronitriol, azo, bis, iso, butyronitriol. Butyronitriol. Yeah, there we go. Okay, azo, bis, isobutyronitriol. So isobutyronitriol is nitrile with but, 4 carbons attached to it. So there's my 4 carbons. It's iso because it's an isomer of it. Azo, because we have a diazo group present, which is just N attached to N. Then we have bis isobutyronitriol. We have 2 of these groups. Okay. This is a pretty cool molecule because if you treat this with heat, it will undergo a series of homolysis reactions, well, really just 2 homolysis reactions to generate 2 equivalents of a pretty stable radical, like you couldn't handle it, but you generate 2 of these. This is an isobutyronitriol radical, and this doesn't have much captative stabilization, but we have an electron withdrawing group attached to a carbon with 2 additional substituents, which are just methyl groups. But that's enough stability to make it so that this will hold on and go for the ride. Now, what kind of ride do we want this to go on? Well, if you heat this up, you will generate this isobutyronitriol radical intermediate, where we could take the AIBN radical and react it with something else. So AIBN plus tributyl tin hydride will generate a pretty cool radical. That is AIBN plus radical plus heat will generate a tin radical. Now, as we mentioned before, substitution and moving down in the periodic table makes for a stable radical. So what happens is this carbon radical sees that opportunity and it pulls off the hydrogen of the tin hydride to generate a free radical intermediate. Now, this free radical intermediate now is going to do something pretty special. This tin free radical will react very selectively with a haloalkane to do what's called a halogen abstraction. And it's due to the fact that tin will form a stable bond to halogen atoms. So what we can do is we can let the halogen come over and attack the tin, and then a radical is going to go on to the R group that was attached to the halogen atom. So our haloalkane actually serves as a precursor for R dot. And this is a general then procedure a general procedure for forming carbon-free radicals. Okay, from any haloalkane. So it's a series of very deliberate approaches. We've got our AIBN, which we can just heat to generate a radical, which then makes a radical with tributyl tin hydride, which then makes a radical from a haloalkane. So it's a series of steps that can happen in very complicated scenarios. And this is proven to be highly useful and highly robust and reliable in more complex synthesis strategies. And so we could look at an example of this where what we could look at is the Barton-McCombie reaction. So example, the Barton-McCombie reaction. This was an important reaction. This is an important reaction because it allows for the deoxygenation of alcohols. This reaction emerged during a time when we were uncovering a lot of truths about organic chemistry, but things like, and let's just, I don't even need the CH2 group here, but things like worrying about how many atoms you put into the reaction and how much waste you generate weren't necessarily the top priority. Rather, it was the overall transformation. So this is another one of these complicated mechanisms, fun to teach and talk about, but holy cow, there's a lot of waste and reagents that are required. And that's kind of an issue with the AIBN tributyl tin hydride approach. Okay, so what we do in this reaction is we deoxygenate an alcohol. In step one, we treat this with sodium hydride, and then the thiol version of carbon dioxide. Oh my gosh, CS2. Gosh, I'm forgetting what this is called. It's just blanking on me. We also need some methyl iodide present. And then in step two, we go AIBN tributyl tin hydride. And here we're not going to take advantage of forming a halogen intermediate, but rather we're going to rely on another stable bond that tin can form, which is a tin-sulfur bond. But this will ultimately give rise to a deoxygenated alcohol where the hydrogen, a hydrogen replaces the oxygen group, which if you can imagine, I don't really know any other great ways to do this off the top of my head, replace an oxygen with a hydrogen atom, okay? So what we do in this reaction is if we focus on step one, ROH is going to see sodium hydride and form a sodium alkoxide. You could have cross out the sodium if you want temporarily. Hydrogen comes in and pulls off hydrogen. So this is just sodium hydride being a base. Now our alkoxide countered by sodium is a good nucleophile, and CS2 is actually easy enough to get our hands on. Carbon disulfide, gosh, carbon dioxide, why not carbon disulfide? Jeepers. Okay, so we can add the carbon disulfide, and you can put carbon disulfide into a bottle. It's not as low boiling as carbon dioxide. And it's a good electrophile at carbon, just like any other sp hybridized carbon would be. And when we add, we push the electrons onto sulfur to get this intermediate, which then reacts with methyl iodide, sulfur being a good nucleophile. We'll add to methyl iodide, displace iodide, and generate our key sort of, that should be a methyl group, or sort of like dithiocarbonate structure. And it's the sulfur atom, the thionyl, looks like a carbonyl. It's not an oxygen, so it's a thionyl, I guess, a sulfur carbon double bond. That's what's going to engage our tin species in a radical pathway. So now in step two, AIBN, much like we just mentioned, plus tributyl tin hydride will generate SnBu3 radical. Now the SnBu3 radical is going to interact with our thiocarbonate to make a species that has a tin sulfur bond attached. Okay, and then we have a carbon-centered radical as a result. So that's using fishhook arrows to give rise to a carbon-centered radical because the tin forms an actually fairly strong bond to the sulfur atom and gives way to or loses a sort of weaker pi bond, the carbon-sulfur pi bond. Well, now we set up a series of arrows where we could have here to here, carbon to oxygen to form a double bond. To do that, we need to steal an electron from the RO sigma bond and then push the other electron onto the R group, and that's going to generate our R dot. And then R dot is going to react with tributyl tin hydride to give rise to this intermediate. And so how much AIBN do we have to add to these reactions? That's an important point I didn't emphasize. We don't need much AIBN. We don't need usually a stoichiometric equivalent. We just need enough to initiate the reaction. And then we typically, if we need a hydrogen, we can just pull it off of the tributyl tin hydride at the end of the reaction. So there's a specific example of a reaction that uses tributyl tin hydride, but you could do some cool stuff with tributyl tin hydride and AIBN, where AIBN is the initiator. I'm going to capture that here as well. So AIBN is the initiator. Let's just take, for example, if we have a this species where I have a bromine atom 1, 2, 3, 4, 5 atoms away from an alkene, 6 atoms away from the end of the alkene, and we add to this AIBN as an initiator, which means we add a less than stoichiometric amount of AIBN to the reaction mixture, but we don't use it as a catalyst. We use it to just kick the reaction into gear. Tributyl tin hydride will add as much as we need. Not a great thing to have to deal with in the environment, but it gets the job done for this reaction. What we can do in this reaction is generate our tributyl tin hydride radical, which will abstract the halogen to generate a carbon-centered radical. Okay, and now what we have is a radical that can add to a pi bond to generate a ring. And this is actually going to do actually form a 5-membered ring as opposed to a 6-membered ring. And this is a reaction that is described by a series of studies that led to Baldwin's rules. And what I'm saying is if we wanted to have the double bond get added to the radical at the edge, we would actually get we would see that's not a preferred reaction, or that's a slower transformation, even though it gives rise to a more stable ring. Okay. So this is this is called a 6-endo ring, where you form a ring and you push the charge inside the ring. This is called a 5-exo ring. Baldwin's rule says 5 exocyclizations are favored. In the past, I've touched on Baldwin's rules in a few depths. If you just Wikipedia search Baldwin's rules, you'll see a big chart and it'll tell you when some cyclizations are favored and disfavored. I'm happy to talk about this at more length if there's interest. But then the point of me showing you this reaction is that we can see that the radical at the end of the reaction actually abstracts a hydrogen from the tributyl tin that's left over, and that's going to give rise to our product and generate more tributyl tin radical to keep the reaction going. So we only need the AIBN as an initiator. Okay, so that'll do it for radical chemistry and for the lectures for this week. There's a lot more to do with radical chemistry, and there's a lot more really interesting things that are emerging. For example, people are learning ways to take carboxylic acids and convert those into radicals through a decarboxylation route. You could take a carboxylic acid, remove CO2 from it, and the alpha position next to the CO2 group is where the free radical is. And so that turns out to be something you can do a little bit more greenly. That is, carbon dioxide is the byproduct. We have too much carbon dioxide as it is, but in terms of toxicity to the environment, if we figure out a way to get carbon dioxide under control, carbon dioxide itself is not, bad. It doesn't like kill people. Well, gosh, I gotta be careful. Okay, I should just end the lecture now. Okay, so that'll do it for this week's lectures. Have a great week, everyone.